Now, let us discuss a little bit about the experimental procedures for studying properties of individual molecules. Now, experimentally, it is necessary to work with a macroscopic sample. So, Avogadro's number of molecules in the container, and number of molecules, call it M total, number of molecules, is very large. In such experiments, which are designed to investigate properties of individual single molecules, the sample is in the gas phase under ideal gas conditions, which means temperature is not very low and the pressure is not very high, so that intermolecular distances are relatively large. This is needed because otherwise it may be necessary to take into intermolecular interactions, and that's very difficult. So the situation should be such that intermolecular interactions should be negligible. Even though the ideal gas conditions allow us to ignore the intermolecular interactions, nevertheless, we have to keep in mind that the molecules inside the sample are colliding with each other. So what happens is that a molecule initially in a certain energy level, if you imagine what would happen as time goes on, because of the collision of the molecules, energy transfer from one molecule to another one is possible. So that the energy level of the molecule would be changing. Now, this type of collisional fact is expressed by the concept of temperature, absolute temperature. We can imagine that when thermal equilibrium is reached, the number of molecules at a certain energy level should be no longer changing. So it is the absolute temperature in other words, Kelvin unit. In thermal equilibrium, at a given temperature value, the average number of molecules in a certain energy level should be constant. And we call it the average value, or or average number of molecules with energy E sub j, j energy level. This is in a sample at a given temperature. It's called population of energy level EJ. Remember, previously we talked about occupation numbers of an energy level. This concept is very similar to get idea. In fact, it's almost the same thing. So E1, E2, E3. For example, this diagram is showing that there are two particles at energy level E2. No particles in energy level E1, no particles in E3, and so on. So the population of energy level E2 is 2 here in this example. Of course, in the macroscopic sample, the number of particles, the number of molecules is very, very high. It's of the order of Avogadro's number. And therefore, the population of the levels, the population of some levels would be very high. It will depend on the absolute temperatures also. Okay. Now using this idea, population, we use the symbol capital N, J. It's a number. Of course, it should be an integer by definition, a whole number. But when the numbers involved are very, very large, then in our expressions, we could obtain some fractional numbers, but just remember that definition is required. It must be an integer, because we are just saying how many particles are there in that energy level. That's necessarily a whole number, integer. Now, this number of molecules, average number of molecules, or population of energy level in a sample, which is in term, it will be the absolute temperature T, is given by the Boltzmann distribution, which is a constant times the generous of the level times e to the minus Ej over this is called Boltzmann. Distribution. C is a constant. Let us say proportionality constant. In this expression, the change in quantity is the J quantum number. Right? And when J changes, Ej will change. Right? E1, E2, numbers are changing. Now, this value of this constant is the same for all energy levels. Here, Gj, G sub j is degeneracy of level, energy level, E sub j. T is the absolute temperature, and this quantity is called Boltzmann constant. This is the standard gas constant. Remember the symbol capital R? Per molecule. So it is gas constant divided by Avogadro's number. Numerically, it is 1.381 times 10 to the minus 23 joule per Kelvin. This factor here is the exponential term, e to the minus energy divided by kT. That quantity is called Boltzmann factor. Now, the exponent in the exponential is this ratio. Let us first analyze the units. The expression is e to the minus x. So this is x here. X should have no unit, dimensions. All right. What does it tell us? We know that energy has a unit. Energy has energy units. Therefore, the denominator, which is K times T, also has a unit. And what unit it must have so that X will have no unit? KT, K times T, must have energy unit, isn't it? You see it from the definition of KB. This P as a subscript, capital B, is attached to this symbol to, so that it just like K, you may mean many different things. So specifically to this number, the B subscript is attached. But when I discuss it, I don't say KB times T, I just say KT. Because we are talking about, we know what K is, Boltzmann constant. All right. This has energy unit. Same unit as this one. If we are using SI unit, then energies will be expressed in joule. So K times T will have joule. You see, from the unit of Boltzmann constant, it is joule per Kelvin. And if you multiply the temperature, you have joule. And you can see that in the image. Now, this quantity is a useful quantity. It gives us a measure of thermal energy. So, we say when the energy level is high relative to the thermal energy or low relative to the thermal energy, meaning the value of x is a large number or a small number. Now, this is the Boltzmann factor, e to the minus x. X is a positive number. This number is a positive number, and KT, of course, is positive, which means x is always positive. Now, what is the graph of e to the minus x? We are looking at this part. The exponential function e to the minus x very rapidly goes to 0 as x becomes large. So, large x means high energy level. EJ is large, isn't it? Relative to KT. So, this graph is telling us that Boltzmann factor is going to be very, very small. In fact, near 0 for high energy levels. Right? If this factor is 0, 0 times anything is 0. So, population of high levels is negligible. We see it from this expression. Do you see it? We just examine the graph of e to the minus x, and for which numbers x, these factors becomes very small. Here's the graph. Large x means high energy, high value for the energy level. And for large x values or high energy levels, the Boltzmann factor is becoming very, very small. It means the population of high energy levels is very, very small. Only low energy, say the ground state, maybe first excited, second excited, a restricted set of energy levels are significantly occupied. Very high energy levels are never occupied. That means, imagine the molecules inside this cell. Number of molecules at a certain energy level is given by this expression. So, some molecules in the sample will be in this energy level. Others will be in that energy level. Still others in that energy level, and so on. very high energy levels are empty because the Boltzmann factor is near zero. So relative distribution of the molecules into the available energy levels is given by this expression. Now, this is directly the number of energy level EJ. For that, we need to know the proportionality constant. In practice, we talk about relative populations. These are populations relative to the lowest level. When the energy levels are numbered like this, starting with 1, E1, the lowest level is called E1, the next one E2. Then we are talking about this expression, Nj divided by N1. All right. And this is, we use this expression for both Nj and N1, so the C, proportionality constant, cancels. And we have and this can be simplified. So, this energy here is the relative energy of the jth level relative to the lowest. So, for instance, this E3 minus E1 is this relative energy. In other words, in a way, you take the lowest level as your reference point, say assign 0 to it, then measure all the other energies relative to the lowest one. That's what you see here. Now, from this expression, you should convince yourself that at t equals 0, absolute 0, this quantity, which is Ej minus E1 divided by Jt, if the upper part is non-zero, but if t is 0, absolute 0, what will happen? Non-zero divided by 0 will give infinity, plus infinity. If x is infinite, the Boltzmann factor is going to be 0. Therefore, all levels Ej, which are higher than E1, will have 0 population at absolute 0. the E1 itself, if you put E1 minus E1, what will happen? You will get 0. 0 divided by some numbers, when we say, of course, in such expressions, we don't directly put the numbers. In other words, we don't get put 0, 0. But we put a number which is very near 0. For example, put 10 to the minus 6. 10 to the minus 6 is a very small number, isn't it? But if the upper part is 0, 0 divided by 10 to the minus 6 will give 0. E to the 0 is 1. So, at absolute, the situation at absolute 0 is that all molecules are going to be in the lowest energy level. All of them. Say this level. Avogadro's number of molecules could be present in it. At absolute 0, all these molecules will be in their lowest energy level. What do we call the lowest energy level? Ground energy level, isn't it? And populations of these means, if all molecules are in the lowest energy level, it means there are no excited molecules at absolute 0. Populations, this will be, the populations with this factor is going to be 1 at absolute 0, and for all the remaining levels, it will be 0. We are going to use this expression, the Boltzmann distribution, for several types of energies. I will start with applying it to the rotation energy levels, but same expression can be applied to vibrational distribution of the molecules and also the electronic distribution of the molecules. But before that, it is useful to consider some non-standard units for frequency and energy. Even though they are not non-standard, a lot of people are using these non-standard units, and therefore you should get used to it. The unit is wave number unit. This unit is used for both frequency and also energies. First, let us define the unit. These definitions come from properties of light. And then they are generalized to normal particles. Now, we know from property of light that frequency of light times its wavelength is equal to a constant. It simply means frequency and wavelength are not independent. If you know one of them, you also know the other. This expression can be written where this symbol is just 1 over lambda. Now, if you use SI units here, then unit for distance is meters. So the unit of this quantity is 1 over meters if you use SI units. This is frequency in hertz. And you see from this expression, frequency is standard frequency, or using the standard unit, SI unit, hertz, is directly proportional to this quantity, in which speed of light, c, is the proportionality constant here. Unit for the left side is hertz. This one is 1 over meter. So this relation is telling us that instead of using the hertz unit for frequency, it is possible to use 1 over meter unit using this definition, because whenever you need it, you need the hertz. Here is the conversion. You just multiply the numbers with this unit for the frequency with speed of light, and you can always obtain it in hertz if you want it, or if it is needed. Now, in the practical applications, chemists, instead of using 1 over meter, they use 1 over centimeters. So, very frequently. And in the majority of the textbooks, if the wave number unit in words, wave number is used, they 99% of them mean 1 over centimeters. They do not mean 1 over meter. It's just some kind of getting used to it. Now, what is the 1 meter is 100 centimeters conversion, isn't it? So, using wave number units is no problem. Whenever you need to change from wave number into standard hertz, 1 over second, you use this expression. But you just remember that value of c should also be in centimeter per second, which means the SI unit, SI value, 3 times 10 to the 8, should be multiplied with 100. Or, what does it mean? You just use 3 times 10 to the 10 centimeter per second in the conversions. All right, this definition of wave number unit, which arises from the relation of the frequency wavelength of light, is generalized to all kinds of frequencies. For example, molecules, our material molecules, have vibrational frequencies. They vibrate. Take a diatomic molecule. There is a vibrational motion. Vibrational motion means there is a corresponding frequency of vibration. And vibrational frequencies can be obtained experimentally using infrared spectroscopy. So they can be obtained. Those experimental values are always reported using this wave number unit. When you look up any physical chemistry textbook, look up vibration frequencies. You will have table of frequencies for a list of molecules. You will see over there the numbers are given in centimeter minus 1 unit, wave number unit. So you should get used to it. For example, go ahead. Yes, I do have an example. Hydrogen chloride molecule. Vibration frequency of this molecule is universally reported like this. Near 3000 in wave number. In the tables, you will see this number with this unit here. Now, for some reason, if you want to express this frequency in the SI unit, what do? You take this number, put it here, and multiply with C. But you should use, for the numerical value of C, 10 to the 10 factor, because the standard value is, the unit is meter per second. However, in the conversion from wave number into Hertz unit, you should make sure that the value of C is also in centimeter per second. Centimeters per second times 100 centimeters. Okay, this is how it is converted. Sometimes you need to go to in the opposite way. Frequency could be given to you in the SI unit, Hertz unit. You may want to obtain the wave number value. Then you just divide it by C. C in centimeter per second unit, 10 to the 10 factors. Then you will obtain the frequency. Now, the same unit, wave number unit, is also used to express energies as an energy unit. Again, the idea comes from properties of photons. Energy of a photon is h times frequency, here a frequency in Hertz unit. Then we can replace this frequency in Hertz unit by wave number unit using this expression. Now we see that this is proportionality factors. Or conversion factors. So, does it say? You can use wave number unit as energy unit also, in addition to frequency unit. For example, this number here, I said it is the vibration frequency. Now, what is the corresponding energy? I will say the energy involved here is also this number, same number. When I want to express it in SI units, if I mean energy by this number, I use this conversion factor, H times C, multiply that number, 990, with H times C, then I will obtain the SI unit joule. Okay? And it will be energy. In fact, it is the that number is the spacing between one vibration energy level to the next one. Vibration energy levels are equidistant. But I can also use, I may interpret it as frequency. And in that case, if I want to find out what is the SI unit value, conversion factor is C. Just C times that number will give me in hertz. Now we can continue with the Boltzmann distribution. You consider hydrogen chloride gas, in which this is chloride 35 isotope. Hydrogen has three isotopes. One is hydrogen, mass 1. The other is deuterium. But usually masses of hydrogen are indicated by different symbols, like hydrogen, mass 1 hydrogen, mass 2 deuterium, mass 3 tritium. All other elements in the periodic table, the different isotopes in the periodic table, use the same symbol, for example, chlorine, and then attach a left superscript, which tells us the mass number of the isotope. So, okay, now for this molecule, value of B is 10.397 wave numbers. So I'm using the wave number unit in reporting the rotational constant of HCl molecule. Am I using the wave number unit, centimeter minus 1, as a frequency unit or as a energy unit in this example? Remember the definition of B. Or remember the does J have any unit? What are J? J are just integers. You know the unit of the left side? Energy unit. Therefore, units for B must be So, from that information, you should understand that I'm using the wave number unit in this expression as energy or frequency unit. Energy, what is the conversion factor? H times C. So, if you want to express this value in Joule, what is the conversion factor? Planck's constant times C. Multiply it and then you will obtain it in Joule. Okay. Now let us take the temperature. T is 300 Kelvin, which is room temperature. Now, Boltzmann factors contain, when we apply it to the rotation energy levels, Ej minus E0. Remember, is relative. Relative populations using the J symbol. Jth number of molecules in the Jth level divided by the lowest level population, because energy levels, rotation energy levels are numbered here according to J values, and J starts with 0. You should make the necessary adjustment in the notation. So we have J level minus the lowest level. The lowest level is E0. In fact, the numerical value of E0 is, what is it? For J equals 0, what do you get? 0. This is 0 divided by in the calculation, if, well, Ej is this value, and if B, unit for B is wave number, then you should convert this expression, KT, into same unit also. So, for 300 Kelvin, for K, you use 1.381 times 10 to the minus 23 joule per Kelvin. If you multiply, you will obtain this number in joule units. To convert it into wave number unit, just divide this with H times C, and this will give you. When you do this, you get 208 wave number. Energy, wave number as energy, and this is also wave number in as energy. Now this way, we can continue the calculation of these values. E is as this number, and KT in wave number is the thermal energy, 208.6. So those energies which are larger than 208, or much larger than 208, will have very large exponents, both, because Boltzmann factor is e to the minus x, the populations will be small, only for energy levels which are nearby the thermal energy, 208, will have significant populations. But we will continue.